Suddenly the class stopped because I couldn't keep the track of the I couldn't keep the track of what I was couldn't keep the track of the time. Sorry. So again, I'm writing sudden interruption in the process. So I'm going to write the last part once again. Just give me a second. So I was writing this. I was proving the third property. And
fourth, sir.
Fourth property. And just a minute. AKI bar and AKI, which is equal to summation over IK mod of AKI whole square. And what I was saying that if A is not zero matrix, A is not zero matrix, then AKI, these elements are not equal to 0 for some K and I. So the inner product of the matrix with itself is always positive. And therefore, V M n cross n F is known as inner product space under the inner product A comma B trace of B star A. Okay, this inner product is a special inner product which is known as Frobenius inner product. Frobenius inner product. So in the previous class, we have come across the inner product which is called standard inner product, and now we have come across an inner product which is called the Frobenius inner product. So always remember that when we talk about the vector space Fn, we always consider the inner product of the form AI bi bar, which is called the standard inner product. Remember, that means if we talk about a two-dimensional space, or if I talk about a three-dimensional space and so on, n-dimensional space, we always take into consideration the standard inner product. But when we talk about the matrix, square matrix, then the inner product that we consider is trace of A star B or B star A, whatever, B star A, which is called the Frobenius inner product. So two different types of inner product that have been defined in this particular class. One is standard inner product, another is Frobenius inner product. Very important, two inner products. These two inner products are actually very important. Okay. Now, let us rewind some of our knowledge before I go to the next session, next problem. Revise our knowledge of some things first of all, and then I'm coming to do the next problem where I'll select a vector space on which another inner product will be defined, and we'll show that inner product, under the inner product, that vector space is also inner product space. So first of all, I'm going to give you some sort of prerequisite over here at this point. What sort of prerequisite I'm giving? If you recall the contents of the first chapter, in first chapter, there were several vector spaces considered. Okay. One vector space is of special interest for my next problem, which is as follows. If capital S be a non-empty set, and F be any field. Right now, I'm not talking about the inner product. I'm talking about something. I'm trying to make you recall something from the first chapter. So let S be non-empty set and F be any field. And let SF denote the set of all functions, from S to F. Okay. Two functions F and G are equal if Fx is equal to Gx for all x belongs to S. Okay. The set F S F is a vector space, with operations F plus G of x is equal to Fx plus Gx, which is the vector addition. Here the vectors are the functions, and scalar multiplication is C of F of x, which is C into Fx. First of all, if you have not done the problem earlier, first of all, this remains still as your homework to check that this sort of set F of S, which is a function from the set S, which is a set of all functions from the set from S to F. You first of all, you have to check that, yeah, it is a vector space. It satisfies all the 8 properties. If you have not done so earlier. So that is I'm keeping as a homework again for you. Now, that is the first prerequisite. This is prerequisite number 1. Okay. Section 1.2 of the book that I shared with you. Next, likewise, we know if I consider the set of real numbers, which is denoted by R, this symbol. So if I take capital S to be R and capital F to be R, both are same. The set S is also same, and the field F is also R. They're both same. Then since FSF is the set of all functions from S to F, so FRR will be the set of all functions, continuous, discontinuous, whatever, set of all functions from R to R. Okay, this is point number 2. Now, prerequisite number 3 is go to the subspace section of that particular book. If you have this book with you, in subspace section, that means probably the section is 1.3. I forgot. We assume a set CR which denote the set of all continuous real valued function, set of all continuous real valued function defined in R. Okay, it is quite obvious. So FRR is the set of all functions and CR is the set of all continuous real valued function. Obviously, CR is a subset of FRR. Okay. So your next homework, if you have not done so earlier, is to check that CR is a subspace of FRR. Okay, so if you have not done so, I am recommending you to go through this proofs once again. The proof has not been done in the book, so you have to do it by yourself. These are the 3 prerequisites that will be needed for our next problem. You can write your student IDs in the chat box if you wish right now. Let's come back to our discussion of the inner product space. Okay. So here we consider a set, a vector space, which is defined as follows, denoted by this, which is the vector space of continuous.
Sir, your voice is cracking.
Okay, I'm saying that now. Can you hear me? Can you hear me now?
No, sir, you're clearly
Yes,
audible.
sir.
You're
Yes,
clearly
sir.
audible, sir.
Promise.
Yeah. Can you hear me now?
Yes, sir, you're clearly audible.
Okay. So I'm saying that, have you understood the prerequisites? These are the 3 prerequisites that I need to be, checked. Actually,
So
the
could you explain prerequisite number 1 once again?
yeah, prerequisite number 1 means that you have to check that this type of set from of all functions from the set capital S to the F set capital F, all this type of functions, they are under these operations. This type of set is a vector space. This is the prerequisite number 1. This example is given in section 1.2 of first chapter. Next,
Okay, sir.
next, what you need to check is that next you have to check that you consider this set, which is FRR is the set of all real valued functions, all functions, but CR is the set of all real valued continuous functions. So under the same operation, you need to check that CR is the subspace of FRR. This is probably, this example is present in section 1.3 of the chapter subspace. That has been set as an example. It has not been proved over there. So you need to check that, yeah, indeed CR is a subspace of FRR. Then your understanding of the entire thing that I'm discussing will be complete. Now, if you think that, okay, don't have to do it, as Sir is saying that it is a subspace, then it is a subspace. I'm believing him. Then it is up to you whether you need to be sure by doing the calculation by yourself, or you have to believe me, or that is up to you. My point was the discussion, I was discussing about the inner product space. So keeping these prerequisites in mind, I am considering a set which is denoted by this, which is the vector space of all continuous real valued functions defined in the interval 0, 1. And you know that 0, 1 is actually the subset of the set of real numbers. Okay. We define an inner product, we define an inner product between two functions. Let us name this vector space as V1. We define inner product of two functions f and g taken from V1 by fg, which is the definite integration from 0 to 1 ft gt dt. Okay, carefully listen to me. So this is the inner product that I'm defining on this set capital V1. We want to check that under this inner product, my set V1 is the inner product space that I'm going to check. So let's start. Solution. Number A, take three functions f, g, h from V1. Now linearity property, f plus g, h, that would be equal to 0 to 1 f plus g of t into h of t dt. Now, why this prerequisite is required, you will now be able to understand that. Look at this particular expression, how this operation is defined. Whenever I write f plus g of x, we consider it as fx plus gx for all x. This for all x, and this is also for all x. I'm going to apply this onto this particular expression. Suppose you do not know that this happens, you will not be able to proceed further. So that is why this particular prerequisite one is required for the given problem. Now, as we are actually well informed about this sort of operations defined on the set of all functions from say R to R, or from on CR or on C01, the vector space that I have considered. So now we can write it as integration 0 to 1 ft plus gt, put a bracket, and ht dt. Then you can write it as 0 to ft ht plus gt ht dt. And you know, probably you have already figured out in chapter 3 that the definite integration is linear transformation. So we can write it as, we can separate them. We can write it as 0 to 1 integration 0 to 1 ft gt dt plus integration 0 to 1 gt, this would be ht, and this would be gt ht dt, which is equal to this fh. This is the inner product of f and h, and that is the inner product of g and h. Okay, so for the linearity property is satisfied by this rule. Next, we take the scalar c belonging to f and the function f belonging to V1, g belonging to V1. Then we have CFG, which is integration 0 to 1 CFT GT dt. Again, just look at this expression. This particular expression is actually equal to C into f of t, which happens for all t, gt and dt. And when you know that this constant can come outside the integration sign, so we get C into 0 to 1 integration 0 to 1 ft gt dt, and that is equal to C, the inner product of f and g. Second property is also satisfied. Now let's come to the third property. Complex conjugation of this inner product, F and G. We take FG from V1. We write integration 0 to 1 ft gt dt, put a bar over there, that is equal to integration 0 to 1 ft bar gt bar dt. Why? It is a well-known result that if we have an integration of f some function and the bar is taken, it is simply equal to f integration f bar. It is from calculus. Okay, so I have applied this rule over here, and now we can interchange these two items together. We can write, because they are continuous functions, so we can interchange them. And since they are real valued, so gt bar will be simply as gt, ft bar will be simply as ft dt, and that would be equal to gf. So the third property is also satisfied. Fourth property. Now, probably you have seen, if you have the book with you, probably in the book you have seen that it is written, something in the book it is written. First of all, I am going to write what is written in the book. They have written only one line, one statement, in a single line answer. They have given a single line answer, and they said that A, B, C can easily be checked. For D, we have this. So what they have written, let me write that particular statement first of all. They have written in the book, they have written, if F is not equal to 0, then F square is bounded away from 0 on some sub-interval of 0, 1. Okay, what do we mean by this particular term, bounded away from 0? Okay, F squared is getting bounded away from 0. Let us try to understand this particular term from two aspects. First of all, let me write it in the following manner. F squared is bounded away from 0. By this statement, we mean that its distance from 0 is bounded below by a strict positive number. I don't know whether you know, you are familiar with this particular term or not, with by bounded below or kind of thing, but I try to explain the thing geometrically. This is a byproduct of real analysis. Whatever I have written over there, it's the byproduct of real analysis, and I think this particular thing is not there in your syllabus. Okay, so there is no provision of discussing the terms like bounded above, bounded below kind of thing. Okay, so these are not there in your syllabus. You have to digest it in this manner, or you can recall this particular meaning of this particular statement geometrically. Geometrically, what does this mean?
Hello, sir.
Yes, tell me.
Please show sir, in C property, in last third step, sir, how you can interchange GT conjugate with GT, sir?
It is a properties of the real valued continuous function. If the function is continuous, then you can interchange them. If the function is not continuous, you cannot interchange. Again, it is a result from the calculus, real analysis.
We can interchange GT conjugate to GT direct.
Yeah, so yeah, GT conjugate to GT bar is GT because GT is the real valued function. Therefore, Since GT bar is G
Yes,
is
sir.
the
Yes,
real
sir.
valued function, therefore G bar is G. Okay.
Oh, okay, sir. Yes, sir. Yes.
And since it is continuous, then integration FG dt is same as integration GF dt. If you consider any discontinuous function and you try to integrate it, you know the discontinuous function cannot be integrated easily. Actually, we use the process of Riemann integration for integrating a continuous function, and for discontinuous function, we actually use Lebesgue integral. Lebesgue integration is not there in your syllabus. Riemann integration is also not there in your syllabus in general. So these are all matter of real analysis. We're very critical. I mean, concept is actually very not that easy, but you have to do this particular problem. You have to remember these rules that this happens. Okay, we can interchange, not always, but for the continuity we can interchange. For discontinuity we cannot interchange. So these are actually the matters that are not part of our syllabus. So there is no provision of elaborate discussion of that. So this happens. Have you understood how it happens? Two things is
Yes, sir.
happening. Real valued continuous function. Because of the vector space that we have taken into consideration, for this, I am actually capable of doing this particular operation over here. Similarly, said that right now I'm actually discussing about this term bounded away from zero. It's something which is not very easy to understand. I'm trying to try my level best to understand this particular thing by some geometric figure. In real analysis, it is said that, see, f is not zero. What do you mean by that? First of all, you tell me. Whenever I say that f is not zero, what do you mean by that?
It not passes from origin.
No, this is not the meaning of this. This zero is what? This zero is the zero function, because here zero is not origin. This is not a number zero. It is the function zero. It means f not equal to zero. It implies that, remember, fx is not equal to zero. Zero function means 0x equal to 0 for all x. That is called zero function. So fx is not equal to 0 for all x. So at least one x is there in the domain for which fx is non-zero. Fx is non-zero. Now suppose this is the meaning of this. Now suppose here is a point. What is my domain here? My domain is 0, 1, because the vector space that I have considered here is from the closed interval 0 to 1. Suppose this is the point C at which the function is not having zero value. It is having some non-zero value. So I'm drawing it. Some non-zero value is there for this function. This is FC. Okay. Now in real analysis, another result is there that if you can find such a thing, such a point at which the function is non-zero, and if the function is continuous, you will always be able to get an interval, very small interval, c minus delta to c plus delta. In this interval, this function will remain non-zero, like this. So if this is the midpoint, on the left hand side of it, the function is non-zero. On the right hand side of it, the function is also non-zero. What I'm saying that f not equal to 0 means fx is not equal to 0. Fx is not equal to 0 for all x. That means at least one x is present in the domain under consideration for which fx is non-zero. This means, suppose our domain of consideration is 0, 1. So suppose C is that point at which the function is having non-zero value. So I am considering some value which is given by FC, which is marked by this dotted line. Now in real analysis, there is a very important theorem which says that if such a number exists, such a number exists at which the function is having non-zero value, around this number, we can always find an interval, a very small interval. Delta is very small as you can imagine. This function will remain non-zero throughout like this. Okay. Now, its nature will be preserved. Now, this is not the only case. Here, another instance that I can show you. Suppose this is also the interval under consideration, that is 0 and that is 1. Okay. Now, the function can, suppose this is the point C1 at which the function is having some non-zero value, and this is the point C2 at which the function is having some non-zero value. You can always find an interval around C1 at which the function will remain non-zero, and like this also. So the function value can be negative also, but I'm not talking about whether the function's value is negative or positive. Function value will be non-zero. It can either be positive or it can either be negative. So look at my diagram carefully. Around C, I am always able to find an interval at which the function will remain non-zero. Around C2 again, I'll be able to get a function which will always be non-zero. Okay. When we consider this is all about the function f. So function f can behave like this. Function f can behave like this, that also. Actually, this is more general. The left-hand side figure is more general than the right-hand side figure. Right-hand side figure, I have considered the positivity only. On the left-hand side figure, I have shown you the positive part or negative part also of the function value. So let us consider this. Now, when this is all about the function f. Now, when it is about function f square, when we take the square of the function, what it does, it lifts the negative part into positive part, and we can get a thing like this. We can get either a thing like this, or we can get a thing like this. I'm giving a very brief understanding. This type of, negative portion is there, but when you are considering the f square part, f square will erase the negative portion and it will lift it into the positive part, lifting it into a positive part. Okay. If there are two,
Sir,
yeah, tell me.
but at least one zero value will be occurs between C1 and C2, sir.
No, zero value. I'm not talking about the zero value. You have not got the point. It is not about the crossing of the function. I'm not saying that it will cross the function. I'm crossing about the lines. It will passing through the line, will cut the line at least at one point. That part I'm not considering. I am saying that I'm talking about a very small interval. In very small interval, it is going to happen that if the function remains non-zero, around it, we are going to get an infinitesimally small interval at which the function is going to remain non-zero. Okay. And
Yes,
this non-zero value may be positive, may be negative for the function f. If the function is f squared, if we consider the square of that function, you will get only the positive side. That the geometrical portion that I'm showing you, it's from pedagogical point of view. Many intricacies are there. When we take the square of such function, many things happen, many such other results that are which are present, but I'm not actually in a position to describe that to you right now, because you do not know the background. You do not know what is bounded below, what is bounded above. You do not have the idea of such kind of thing. So very briefly, I'm saying that this is the thing that will happen if we take the square of the function. So we will get on the positive side only. That is not the figure for f square that I have drawn. That is not the actual figure. That is my rough sketch of something like that would happen. That means my point is that means this is what we actually mean by the statement that the function f square is bounded away from zero. I am actually trying to make you understand the statement that f square is bounded away from zero. What do we mean by that? Okay, So this is the meaning of that happens for real valued continuous function. And therefore, and as it happens, as it is true, then we can write that we can take the inner product of these two function of the function with itself. We can write it as integration 0 to 1 ft whole square dt, which will always be positive because f square is always positive. Implies ft whole square is always positive for all t. Okay, and therefore the fourth property is also being satisfied. Hence C01 is the inner product space with the inner product defined on it. Okay, so that is another example of the inner product. This CR, this function, remember, in functional analysis, this type of set is actually called L2 space. This type of set is actually called L2 space. Same thing, which is having some sort of name over here, gets some different
Instead
name.
of writing a sub-interval of closed interval 0, 1, can't we just write open interval 0, 1?
Yeah, sure, no problem. But what is true for the closed interval 0, 1, it's true for the open interval 0, 1. No problem with that. Understood?
Yes, sir. Yes.
Okay. But the thing is
So
complicated.
L2 space is what? Exactly.
I'm saying that in different domain, different subjects, this type of vector space got different name. The vector space that is this inner product space that we have all studied over here in linear algebra, it doesn't have any special name over here in the domain of linear algebra. But if somewhere, say for example, if you read a very good quantum mechanics book, you will find that they talk about the L2 space. And when they talk about L2 space, that means they are talking something about functional analysis. This L2 space is similar to that one. If they are talking about L2 space, that means they are talking about this type of inner product space. But here in linear algebra's domain, this particular inner product space has not got any special name. And just like the standard inner product and Frobenius inner product, this inner product has not got any special name. But somewhere at some point, you may come across this word, this term in your higher studies. So I am just letting you know that remember that this is the subject matter that we have discussed so far is actually the matter of L2 space. Okay. Now less than 1 minute is remaining. Yesterday I made a blunder because time was there, but I couldn't, I forgot and I just left the classroom. You again rejoin.
Yes, sir.
Yes. So you again.
I phoned you later.
Yes. So you again rejoin because I want to tell you something more about some other parts are actually important and needs to be discussed today only.